Alright guys, so as we continue talking about quadratic functions, we need to stop and talk about something called the fundamental theorem of algebra. So a while back, this guy right here by the name of Carl Friedrich Gauss, smart guy, realized something with polynomial functions. So we're talking about quadratic functions, which are polynomial functions. He realized something happens in every polynomial function, and that is that every function's solutions, so the amount of solutions in every function or for every polynomial function, is equivalent or equal to the degree of that function. So, for example, I've got two functions here. We've got x squared plus 2, that's this red parabola, and then we have negative x squared plus 1, that's this blue parabola here. According to this rule, both of these functions should have two solutions. The reason that they should have two solutions is that the degree of each function, the degree of every quadratic function, is 2. So according to this rule, every quadratic function has two solutions. Now, what we have seen through our work already in quadratic functions is sometimes this doesn't happen. Or what you're going to discover is sometimes the solutions aren't real solutions. And we can see that here on the coordinate plane. So for this blue parabola here, the one that is x squared, negative x squared plus 1 rather, this solution we can see, or this for this function, we can see both solutions. The solutions exist on the x-axis. They're the x-intercepts. So we have a solution here, and we have a solution here. So there are two real solutions to this function, which makes sense and defends Gauss's idea of there being an equal amount of solutions to the degree of that function. But we have a small problem, or really a rather big problem, with this function, x squared plus 2. That's this guy right here. Well, this function never crosses the x-axis. So what we have said so far for a function like this is that it has no solution. No solution. But as we're going to see, what's really occurring here is that it has no real number solution. Now, this idea of calling real numbers, so everything from positive infinity, negative infinity to positive infinity, and everything in between, real numbers is kind of a misleading idea because there are more real numbers than what we call the real numbers. And this is where we're getting into what is called imaginary numbers. So it sounds a little misleading. Real numbers, they're the real ones. Imaginary numbers are the imaginary ones, the fake ones. But make no mistake, they're all real numbers. They are observable in the universe, observable in the physics of things. We need them for things like the fundamental theorem of algebra, and we need them for certain things to exist. And even sometimes dealing with imaginary numbers, you're going to end up with real number solutions. And again, it's all real. The name real or the name imaginary just refers to the label that we put on them. But they are all real numbers. And the reason that these have to exist is because of situations like this. There is no number that we can multiply by itself where our product is a negative number. So let me change that to something that we can actually discuss in a little more familiar way, because I know what the square root of 9 is. The square root of 9 is plus or minus 3, because 3 times 3 is 9, and so is negative 3 times negative 3. They both equal 9. But negative 9. There's not a number that we can multiply by itself to get negative 9. However, for the fundamental theorem of algebra to work, which proves a lot of things that we do know to be true. It's not just theory. We have to have a way to answer this. We have to have a number that we can multiply by itself and get a negative number. This is where what we call imaginary numbers come in. So the basic unit of an imaginary number term is I. And I is equal to the square root of -1. And using this, we can simplify negative radicals. So when we're solving a quadratic equation in our arithmetic, we get to a negative inside the radical, and we would say, oh, we're done, no solution. There's not an answer to that. So if we ended up with something like the square root of -9, it's, oh, no solution, we're done. However, now what we can do is we can break this down and say, you know what, instead of thinking of this as a square root of -9, let's think of this as the square root of 9 times -1, because 9 times -1 is -9. And using this unit of the imaginary number, we know the square root of 9, and using this, we also know the square root of -1. So we can pull out that 9 as a 3, and we can pull out this -1 as an I, and say, well, the square root of -9 is 3 times I. We can just treat that I kind of like a variable. 3 times I is 3I. Now, I know this seems a little foreign, a little strange. The more that we work with this, the more that it's going to make sense. But the idea that I need you to get right now, before we start practicing this arithmetic, is that imaginary numbers do exist. And imaginary numbers are real. And I don't mean that as in they're real numbers. They're different than the label of real numbers, but they do exist. And we have to have imaginary numbers so that things like the fundamental theorem of algebra can be true. It's because of ideas like that that we know that the solutions have to exist. And if the solutions have to exist, then our number system has to go further than what we call the real numbers. And so this is that idea of imaginary numbers. So let's back out a little bit and talk about this in a little more detail. So if I equals -1, we can extend this further to things like I squared. Well, if I is the square root of -1, I squared is square root of -1 times the square root of -1. We're just substituting the -1 in for the I. So I times I is the same thing as square root of -1 times the square root of -1. Well, that is just -1. And we know that, I'll give you another example of something that might make a little more sense. The square root of 9 times the square root of 9 is 9, because the square root of 9 is 3, the square root of 9 is 3, and 3 times 3 is 9. So if this is true, then this has to be true as well. And so we can continue to simplify with imaginary numbers idea. So I is equal to the square root of -1, or we could just say I is equal to I and use that as our base term. Like we just discussed, I squared is equal to -1. We can continue this on through the pattern of really any exponent. I cubed is the same thing as I times I squared. Well, we know that I squared is the same thing as -1, so we can substitute -1 in for I squared. I times -1 is just -I. So I to the third power is the same thing as -I. We can go further. I to the fourth is the same thing as I squared times I squared, which is just -1 times -1, and -1 times -1 is +1. So I to the fourth power is +1. This can even be extended further into the imaginary numbers with higher degrees, and we can simplify this using different rules and different properties of exponents. So I to the 232nd power could be rewritten as I squared raised to the 116th power. Because the properties of exponents tell us that a power raised to another power, we just multiply. And 2 times 116 is 232. So these are equivalent. They're the same thing. Now the reason this is so important is because we know that I squared is actually just negative 1. And we know that negative 1 to the 116th power is just negative 1. Because 1 times 1 times 1 times 1 times 1, an infinite amount of times, is just going to be 1. And if we have an even number, 116 is an even number, if we have an even number of negatives, I'm sorry, I just realized my mistake here. This is going to be, positive 1. Because if we have an even number of negatives, the negatives are going to cancel out and the answer will be positive. So I to the 232nd power is just 1. This can also be done with I to the 43rd power. Now we run into a slight issue to begin with here, because I squared can't be raised to a whole number power and get 43, because 43 is an odd number. 2 times, it would have to be something 0.5, it would have to be 21.5, but we don't want to raise it to the 21.5 power. So the way around that is to say that I to the 43rd power is the same thing as I times I to the 42nd power. And then we can worry about this I later on and simplify this the same way that we just previously did. So I to the 42nd power, that's the same thing as I squared to the 21st power, because 21 times 2 is 42. So we can continue simplifying this. I squared is the same thing as negative 1. Negative 1 to the 21st power is negative 1. Now if we bring down this other I times negative 1 is just negative I. So we now know that I to the 43rd power is negative I. And we can continue this idea to simplify really any imaginary number. I'm not really applying this to quadratic functions yet, but before we do that, we need to practice the skills of completing arithmetic or simplifying with imaginary numbers. What we're going to do now is practice that idea, taking imaginary numbers raised to a specific power or other operations with imaginary numbers and simplify them as far as we can, the same way we would simplify something that had real numbers. If we had multiple terms that all had an x, we would want to combine those. If we had terms that were being multiplied, we would want to multiply them. So in the same way that we have to know how to simplify with real numbers, we need to learn how to simplify with imaginary. So that's what we're going to practice. In Canvas, I've included a couple other videos, another really good one on kind of the history of imaginary numbers. I'm a bit of a math nerd, so I enjoy the video. But it's not a boring video. You might enjoy it. It wouldn't be a waste of your time. If you want to know a little more on the history of imaginary and why they have to exist, so some other numbers that we're used to that haven't always existed, like 0. When 0 was first introduced, it was a crazy idea. The same thing with fractions, but comfortable with them because we know they have to exist. We know that there is something between 1 and 2, so we have to have 1/2, we have to have 3/4, we have to have all those irrational numbers. And hopefully we're going to become comfortable with imaginary numbers and understand that just like we need 0, just like we need fractions, we need imaginary numbers.